Hello Minecrafters, and welcome back to another redstone video. Today I'm gonna teach you how you can build any digital redstone logic circuit that you want, like an engineer, like an actual engineer. And I'm not joking, I'm gonna teach you everything that I have learned in a class that I participated in university. And that class basically taught me everything I need to know, like all the basic stuff that is related to designing a real-life digital circuit. And I want to share that knowledge with all of you because why not? So I have prepared a lot of stuff, as you can see, and we were gonna go through all of this together, and hopefully by the end of today's video you will be able to build any digital redstone circuit that you want, like a proper engineer. So yeah, just sit back, relax, get your pen and notebook, and let's jump right into today's video. First, let's talk about binary. Now, binary is very simple, okay? Binary is just another numbering system similar to decimal, but in this number system, it only uses two numbers, 1 and 0, to represent everything. The reason why most digital circuits use binary is because most digital components that are used to create those circuits only have two states, similar to redstone. For example, this piston only has two states. It can either be off or on, like that. Or this lamp right here, off or on. And off can be 0 and on can be 1, similar to comparator, redstone dust, repeater, and all of the other redstone components. And in real life, this is exactly what happens, which is why people use binary. Now, in order to design any digital circuits, or in this case any digital redstone circuits, you need to know something about Boolean algebra. Now, if you don't know what Boolean algebra is, don't worry, I will gonna get to that right now. Boolean algebra is essentially what you use to design any digital redstone circuits or digital circuits in general. Boolean algebra is like normal algebra, but all of the results are either 1s or 0. So yeah, it's just 1s and 0s. There's no like 2, 3, 4, 5 similar to normal algebra. Okay, that's the only difference. The rest is basically the same. It has theorems, it has laws, it has properties, just like in normal algebra. It even has like variables. So here are Boolean variables. We can represent Boolean variables using like symbols. Here I have x, but you can use a, and all sort of other symbols, and these variables can either be 1 or 0, no other numbers, okay, just 1 or 0. The next thing that we are going to talk about is Boolean operations. Now, in Boolean algebra, there are three very simple and very basic and very important operations. We have the NOT operation, and its symbol is this like upper comma. We have the OR operation, which is indicated by this plus symbol, and we have an AND operation, which is denoted by this dot right here. And throughout this this video, I will gonna use these three symbols, because writing this is like writing NOT, OR, and AND is kind of time consuming. Writing this symbol will make the the function much easier to look at. And speaking about function, let's talk about those as well. Okay, Boolean function, what are they? Well, Boolean functions are basically a way for us to express outputs and inputs. The outputs are over here, and the inputs are a combination of Boolean variables. So I have here a, b, c, d, e, and also Boolean operation. So the input of a function is a combination of Boolean variables and Boolean operations as well. I have here two examples, so you can see what a typical Boolean functions looks like, and they look like this. Okay, now we were gonna get into some properties in Boolean algebra, and don't worry, these properties are really simple, and if you want proofs of all of these properties, you can just Google them. Like I was gonna show you the name, like the properties name. What you want to do, if you want to understand this more like in depth, you can search the name on Google and you will be able to find the information that you want. Okay, I was just gonna go through, like give you an introduction about these like properties. Okay, I will not gonna go in depth into like how to prove those properties, because that we're gonna take like a really long time. Okay, first property, the Annulment Law. I think I mispronounced that, but it's not the point here. Anyway, here is the Annulment Law. We have a or 1 equal 1, and we have a and 0 equal 0. And I have here some visualization, so you can see that these laws here are correct. So we have a here and we input a 0 here. As you can see, no matter the input at a, the output will always be 0, because you can understand this simply as a times 0 equals 0, even though this is not a multiplication operation, it's a AND operation. As you can see, it's an AND operation, but it's very similar to you take a number and you multiply it with 0. This, however, is a bit different. With a, not plus, okay, or a or 1 equal 1. And this is also true, because if you look over here, we have a, input a here, and we have a 1 here, a constant 1. And no matter the input, as you can see, we always get an output of 1. And you can, like looking at this redstone, you can clearly see why. Okay, just say right, like this redstone does is always powered by this repeater. So no matter what input this like we give a is, this redstone dust will always be on, which means this redstone lamp will always be on. So that's why this is a thing in Boolean algebra, and only in Boolean algebra. Okay, alright, next property, the identity law. Now the identity law is something like this. We have a or 0 is equal to a, and we have a and 1 is equal to a. And we can clearly see that here. So here's the AND gate, we have output here, and if we put in a, as you can see, the output is similar to a. So a is 0, output is 0, a is 1, output is 1. We constantly give a like a 1 power here, and yeah, as you can see, the output is basically the input. So this explains why a and 1 is equal to a. Now for a or 0 equals to a, as you can see here, we have an OR gate, and we have an input 0 here, and as you can see, the output is similar to the input a. So a or 0 equal a. Okay, next law or property, the Idempotent Law. I think I pronounced that right. But anyways, this is the Idempotent Law. It looks a bit confusing, but basically, if you take a bunch of a and you AND them all together, you will get a. Instead of like in normal algebra, if you take a multiplied by a several times, it will become a to the power of n. But in Boolean algebra, that is not a thing. So a times a bunch of a's, or in this case n a bunch of a's, will always equal to a. And this is also similar to when you use like the OR operation. So a or a bunch of a's together will give us the a again, or more generally, will give us the same symbol back, like a same variable back. So yeah, this one is a bit confusing. So I have prepared here an example so you can see why it is like that. So here I have an AND gate, like a very big AND gate, as you can see. And when we give a equals 0, as you can see, all of the a's are 0, and we get 0. But when we give all of the a's 1, because well a equal 1, Now as you can see, the output is 1, so it's basically a. And yeah, that's basically this part right here. You can have as many like variables here as you want. They need to be the same, right? The same variable. If they are the same, you will get your variable back, similar to OR. So here's an OR gate. As you can see, when all of the A's are 0, we have a 0, which is basically A. And when we activate all of the A, or yeah, like this, and then we OR them together, we were gonna get A, or 1 in this case. So yeah, a very good example, I think. So here are the two circuits for you to see, and you can just follow the redstone line to understand why these two laws right here are like that. Next law, the complement law. Now complement law is very straightforward. We have A, or the reverse version of A. So, and we denote that by having this upper comma here, which is the not operator. So A or not A will equal to 1, and A and not A is equal to 0. And here I have prepared some circuits so you can see. As you can see, we have A here and we have A not. A is 0, so A not is 1, and as you can see, we have a 1, which is exactly this right here. And if I just flick, as you can see, even though A and A not are changing, the output stays the same. It always equal to 1. As for this one right here, it is A and not A equals 0, and here's the circuit. So as you can see, we have A and not A. A is 0, A not is reverse of that, which is 1, and no matter what I do, no matter what A I put in here, the output will always be 0. So yeah, that explains these two. Okay, next one, the double negation law. Well, the double negation law is like this. So we have A not, as you see, A not, and then we not it again, so A not, that will gonna give us A. And you can clearly see that by over here. For not operation in redstone form, we can use redstone torch. So we have one inversion over here and one more over here. Two inversion will gonna give us the same output as the input. As you can see, the output is basically the same as the input, which explains this part right here. Okay, next law, the commutative law. Now the commutative law looks something like this. I mean, it's pretty straightforward, right? You can basically switch place the variables in both instances. So it can either be OR or AND, and you can switch places, like switch variables places. And yeah, that's true, because the actual part, the operation part, doesn't really care the order of the inputs, as you can see. So yeah, this one is pretty straightforward. Okay, next law, the associative law. Now the associative law is a bit confusing. Now for the bottom one is a bit more like normal algebra. We have A plus B times C will equal to A times C plus A times, no, not A, but B times C. Or in this case, we have A or B, and the output of A or B will end with C. That will gonna give us A and C or B and C. So this one is very similar to normal algebra, but the top one is not. Okay, the top one is a bit more confusing. So we have A and B, and then we OR the output of A and B with C. That we're gonna give us A, or not give, but equals to A or C, and the output of that we're gonna end with the output of B or C. This one is a bit more confusing, but essentially you just switch places. So you switch your operators. So here I have an AND operator, you're gonna switch that to an OR operator. If it is an OR operator, you switch it to an AND operator. and you use parentheses to indicate the priority or order. Okay, next law, the absorption law. Now the absorption law looks like this, and I will not gonna prove this, but you can either use all of the stuff that we have talked about or search it up on Google. Okay, but it looks something like this. We have x or a, it's just a different symbol, it's still like Boolean variables. Okay, so x or x and y will equal to x, and x and with the output of x or y will equal to x. Again, if you want to try to prove it, you can use all of the other stuff that we have talked about here or search on Google. Okay, now we have a very important law here, and this law you do need to remember. It is the De Morgan law. Now the De Morgan law looks like this. So we have a or b, and then we not the result of a or b. That will gonna give us a naught and b naught, similar to a and b, and then we not the result. That we're gonna equals to a naught or b naught. Now this one is very confusing, but it is very important. You're gonna use this thing a lot to simplify your Boolean functions down. Finally, we have the consensus theorem. The consensus theorem looks something like this. Very confusing, I know, but essentially this b and c part, you can just remove that b and c part, and you keep the first two parts. As you can see, we have a and b, or a naught and c, and at the output we have a and b, or a naught and c. So we just remove b and c. Again, you can just search on Google on how to prove this. Now we were gonna talk about the most important thing that you need to know in order to design any digital redstone circuit that you want. Truth table. You need to understand truth table. Okay, so what are truth tables? Well, if you have watched any like logical redstone videos or like computational redstone videos, chance of you hearing about truth tables are really high. But I bet that a lot of you don't really understand what are truth tables and how to construct one. So I'm here and I'm gonna teach you how to actually do it. Okay, so here is our truth table. Now this truth table is describing this function right here, and if you remember about functions, it is that thing over there. Okay, so we have our output indicated by this f right here, and we have our inputs, which is just a combination of like a Boolean variables and Boolean operations. Now if you look at this, you will know that this is an AND gate operation, like an AND operation. So as you can see, AND operation here. So we just AND A and B, and the truth table to describe that is this right here. We have the inputs on the left and we have the outputs on the right. So this is like how a truth table is structured, and now I'm gonna show you how to actually make a truth table based on like a general problem. So in order to construct a truth table, you need to follow these three like rules right here. First, let's talk about the input column. Now the input column is equal to n, where n is the number of input variables. So in this example right here, we have at the input we have two variables. So we're gonna have two columns, column A and column B. So yeah, that is input column. Now for output column, which is this line right here, we need m, and m is the number of functions, because truth table is very powerful in a way that it can actually describe the relationship between multiple functions at the output compared to a lot of variables at the input. So that's why the number of columns is equal to the number of functions. So over here I only have one function, f equal a and b. At the output I only have one column. But if you have more functions, you're gonna have more like columns over here at the output. Okay, and finally, this one is very important, the row. How many rows do you need in order to construct a truth table? Well, the row is 2 to the power of n, and if you remember, n is the numbers of input variables. So for example, in this example right here, we have a and b, we have 2 variables. Using that formula over there, we need 2 to the power of 2, which equals to 4. Now let's count. We have 1, 2, 3, 4. So yeah, the number of rows is basically 2 to the power of n, where n is the number of variables that you have, like input variables. And now I'm gonna show you how you can fill in the numbers here in the truth table. You are gonna fill in all of the possible input combination at the input first. Okay, so we have a and b, right? We have 2 variables, and because we have 4 columns, we have in total 4 possible input combination, like unique combination. So we have 0 0, which is one combination, we have 0 1, which is another, 1 0 is another, and 1 1 is another. So with 2 variables, you can have 4 possible inputs combinations, and with more variables, you can have 2 to the power of n possible combinations. So the first step of writing a truth table is to be able to write down all of those possible input combinations, and then you can move on to the output. At the output, it just describes each input combination does. So for example, here's the first input combination. We have 0 0, so the output will be 0. Here is 0 1, so the output will be 0. 1 0 will be 0, and 1 1 will be 1. So the output needs to depend on the inputs, which is why we have functions. Okay, so this function right here will only give a 1 when this part satisfies like this operation, like an AND operation here. I hope that makes sense. I try to explain that like as best as I can. This part is really important because if you can't construct a truth table based on like your problem, you will not be able to go further. So I recommend you to practice this part. Just get a random like digital circuit online and try to map out a truth table, and then check with the answer on the internet, like check like the actual truth table to see if it's correct. You can do this several times and eventually you will understand what I mean. It took me a lot of time to master this, or not really master, but to understand this when I was participating in that class. But it's really fun, trust me. Okay, now the final thing that you need to understand. Okay, and after this we were gonna get into like a proper example of how to build a digital circuit on your own, like an engineer. Okay, so the final thing that you need to know is Karnaugh's map. Now Karnaugh's map is essentially a different way to see the truth table. On the left we have the truth table, and on the right we have the Karnaugh map. Now even though the Karnaugh map looks pretty stupid, it looks like really complicated, these two are basically the same thing. Like these two things both describe that function right there. Now I'm gonna explain like the structure of a Karnaugh map. So here we have the function, and here is the outputs. Each of these square right here is the one of the output of the function. So as you can see, we have 0 0 0 1, and if you look here we have 0 0 0 1. So yeah, it's just all of those squares there are basically the corresponding outputs at the truth table. Here are the indexes or the coordinates. So for A is 1 0, B is 1 0 as well, and then each square, okay, each square in here is actually corresponds to a row in the truth table. So for example, we have this square right here. The coordinate of this square is 0 0, B equal to 0, and A equal to 0. So we search in the truth table where A is equal to 0, and b equal to 0, we get a 0, so we're gonna write a 0 here. Or for example, this right here, we have this square has b equal 1 and a equal 1. So we look for a equal 1 and b equal 1, a equal 1, b equal 1, and the truth table tells us that f will equal to 1. So we're gonna write a 1 here. And that's pretty much what a Karnaugh map is. It's just a different way for us to write the truth table and a different way to describe a Boolean function. Now that you have understood basically all of the knowledge needed in order for you to build any digital redstone circuit like an engineer, we can now get into a proper example. And the example that I'm choosing is a full adder. I will gonna guide you through how you can design a full adder using all of the knowledge that you have learned in today's video. First step is to analyze what is a full adder. A full adder is a digital circuit that allows you to add two 1-bit numbers together. It also has a carry-in bit, and a full adder has two outputs, a sum, which basically means the sum of the two bits, and also the carry out bit as well. Our job is to design a digital circuit, basically the circuit inside of this black box, so that when I flick these levers, we will get the corresponding output. So the first thing that you need to do in order to design a full adder in this case is to analyze the problem and then convert that problem into a truth table. Now this part will gonna vary depending on your problem, but in this case, since it's a full adder and I know what the problem is, I can come up with a truth table like this. So this is the truth table which we're gonna describe the full adder. If you look at this truth table, you can essentially create a digital circuit that follows this truth table, and if you follow the truth table correctly, you will be able to design the full adder. Again, in order to make a truth table, you need to first analyze all of the inputs and then also analyze all of the outputs, and then you need to see the relationship between the outputs and the inputs. Now over here we have two functions s and that carry out, which is the outputs of the full adder. As you can see, we have two outputs, so we have two functions in our truth table, and since we have three bits, we have a bit, b bit, and also the carry-in bit, we have three columns for the inputs of the truth table. Then we just map out all of the possible input combinations, so we go from 0 0 0 all the way to 1 1 1, and then we're going to describe, like see the relationship between each of these output function compares to the inputs combination. For example, ABC is 0 0 1, only the S output will be 1 or on. If you keep following this, you will be able to construct the full truth table. After you construct the truth table, you have two ways of designing a digital circuit for your problem, in this case a full adder. So the first way, where you basically from the truth table you derive a Boolean function like this, and then you're gonna use these laws right here in order to simplify the Boolean function down, or you can use Karnaugh maps to simplify the Boolean functions down, and I will gonna teach you how to do Karnaugh map simplification. Now if you remember from Karnaugh maps, you can see that we can turn truth table into a Karnaugh map, and each of the functions can be described using a Karnaugh map. In this case, we have two functions, so we need two Karnaugh maps. The first Karnaugh map will be for the sum or the S output, and here is the Karnaugh map for 3 bits ABC, 3 inputs. Okay, now you don't have to remember the size and also the indexes of a Karnaugh map, you can search it up on Google because it's much easier to do that, but I have done it for you to here. But if you need, for example, a bigger Karnaugh map, you can just search it up on the internet and you will be able to find your desired Karnaugh map size. Now back to the truth table, we are now gonna look for all of the input combination of A, B, and C, which gives us 1 at the S output. So I can see 0, 0, 1 and 0, 1, 0 and then 1, 0, 0 and also 1, 1, 1. So we're gonna write those ones in. So first is 0, 0, 1, we write the 1 here, and then we have 0, 1, 0, we write another 1 here, and then we have 1, 0, 0, which is here, and finally we have 1, 1, 1, so we write a 1 here. Similarly to C, we do the same thing. We look at C, and then we were gonna find all of the input combinations which gives C a 1. So here I can see A, B, C equals 0, 1, 1, which gives us a 1 at the carry out, and then 1, 0, 1, another 1, and then 1, 1, 0, another 1, and then 1, 1, 1. So we're just gonna write all of those 1 in. First is 0, 1, 1, so we have a 1 here. Then we have 1, 0, 1, so 1, 0, 1, and then we have 1, 1, 0, which is this, and finally we have the final combination, which is 1, 1, 1, so we write a 1 here. These two Karnaugh maps basically describe the S function and the carry out function. In order to simplify the Boolean function using Karnaugh maps, you first need to circle all of the ones. However, there are some conditions. First of all, you need to circle the ones, all of the ones that are next to each other, either horizontally or vertically. In this case right here, we don't see any of that. So what we can do is we can just circle, like we can circle the ones like this. Only one ones in here. There's only 1 in there, and same thing for all of these 3, just like that. Now there are other cases. For example, over here we can see that there are some ones that are next to each other horizontally and vertically, as you can see. So what you can do is you can circle all of them. You can do like this. But the number of ones that you can circle also has a condition. Okay, so as you can see over here, I only circled 2 ones. Why can't I circle this one as well? They are next to each other, so I should be able to do that, but I can't, because the number of ones that you circle needs to be 2 to the power of n. So n can be from 0 all the way to infinity, but you have to do it in a 2 to the power of n numbers of ones. So it can be 2 ones or 4 ones or 8 ones, 16 ones, but you can't circle, for example, 3 ones in a row, because that is illegal. It violates the 2 to the power of n rules. So here I can also circle these 2 ones because they are next to each other, like so. And I think I'm gonna use a different color wool because it will be easier for us to see in the future. So I'm gonna do this like that. I'm gonna do this as well, so you can see that we can circle these 2 ones, and similarly we can circle these 2 ones as well. So let's do that. I'm gonna get a different wool color, and we were gonna do the same thing like that. Okay, so we have circle all of the ones here and all of the ones here. Now from the Karnaugh maps, you can convert it back to Boolean functions, because that's actually what we want. We want the Boolean function. So how can we, from the Karnaugh maps, get our Boolean function back? Well, it's very easy. We first look at all of the ones, and then we're gonna look at the coordinates. So for example, this one, we have 0, 0, 1, right? So what you need to do is, if the number you see is 0, you're gonna write the inverse of that variable. So in this case, we have a equals 0, so we're gonna write a naught. Similarly, in here we have b and c, so we're gonna write b naught c. What that will look like is something like this. So for the first one, you're gonna get this 0, 0, 1, a naught, b naught, c, because a is 0, so we're gonna write a naught, b is 0, so we're gonna write b naught, and c is 1, so we're gonna write c. And you keep doing this for all of the other ones as well. And from this Karnaugh map, you will be able to derive this Boolean function right here. Now for this Karnaugh map right here, it is slightly different. What you need to do is you need to compare the two bits together to see if they are similar or not. I'm going to show you exactly what I mean there. So for example, we have these two ones right here in the orange circle. We can see that b and c are exactly the same because they are in the same column. But for the rows, we have a equal both 1s and 0, which is invalid. And when you see an invalid situation like that, you can just remove that variable. So in this case, in the orange circle, what you're gonna write is the common variables, the variables that are not deleted. Okay, so a is gone, but we still have bc because these two ones share the same bc, and b is 1 and c is 1. So for the orange circle, you can write b and c. Because a is different, it cannot have both 1s and 0, we can remove a. But b, c, they are similar, and because they are both 1, we can write b and c. Now you can follow this logic for all of the other circles. So from these two Karnaugh maps, we have derived two Boolean functions, and these two Boolean functions are used to describe our further properties. So now if we just follow these two Boolean functions and build the digital circuit using logic gates based on the Boolean operations here, we can essentially create the further. I'm gonna do this one first for example, so you can see how exactly you can do it. So we have a naught and b naught and c. So we have a here, b here, and c here. Now what we can do is we can use Boolean operations. So we have not operation and AND operation. So here, let's implement that. Here we have a naught and b naught. So what we can do is we can have an input lines right here, and because we need a naught and b naught, we can just use redstone torch to invert a and b. And now we have an AND gate with 3 inputs. So what we can do is build a giant AND gate with 3 inputs. So what we can do is like this. We can do an AND gate. I didn't mean to do that. So AND gate like that. I'm gonna remove this like so, and we're gonna wire this like this. Get a we're gonna invert again because there's an AND gate, and here is our output. So this should describe a naught, b naught, and c. So if we provide 0, 0, 1, right, we should get an output. as you can see, we have an output because 0 naught will become 1, B naught will become 1, and C1 will be 1. So all are 1s, and we will get an output. Oops. Yeah, we're gonna get an output. And now what you need to do is do the same thing for all of the other like pairs of input combination. Same for this one, and by the end you will be able to build your very own full adder. And I think I'm gonna stop there because I think I should leave it there as like homework for all of you. It's much more interesting for you to do it by yourself. I have provided you with the Boolean function. You just need to follow the Boolean functions, and hopefully you will be able to design your very own full adder by using all of the knowledge that we have gained in today's video. Thank you very much for watching today's video. I know it has been quite a while since I last uploaded, but I was really busy with university and I did not have a lot of time to record, so yeah, I'm very sorry about that. I will try to record more videos in the future, and hopefully things will be more like manageable in the future for me to upload more videos, because I really love making these sort of videos for all of you to enjoy. They are educational and I think they are fun as well. If you like today's video, consider giving this video a like, and if you want to see more of my content, you can subscribe to the channel. I will provide a world download to this world so you can see all of the laws here, or the Boolean laws here, also the Karnaugh maps, and also truth tables, and also you can try to finish the full adder that we're gonna leave it here. We're not gonna change anything. This is homework for you if you want to fully understand all of this. Okay, again, thank you very much for watching. I really appreciate it, and I will see you in the next video. Have a nice day, everyone.